Okay, what's up?
Hi.
Yeah, I'm Brandon. I'm a founding engineer at O1 Labs. Now I'm the CEO. It's been a lot of years. We built Mina. We incubated Mina. We continue to work on it. Now it's this big project, and there's lots of people contributing. Today I'm going to talk about proof singularity in a lot of different places, I guess. So at O1 Labs, we're really excited about this this internet that I think a lot of people in ZK are working towards building, where developers can use programmable cryptography, ZK, MPC, FHE, et cetera, to create more powerful applications. And we think that Mina plays a big role in this. Why? Because of decentralization. So most blockchain systems, they tend to trade off between scaling and decentralization, and with ZK, you don't really have to make that trade-off. The way, I guess, like the biggest way in which Mina does this is through succinctness, having a succinct blockchain. So I'll just quickly explain what I mean by that. But first, ZK rollups. What's a ZK rollup? You have a bunch of transactions, you prove them with ZK, and then you post the proof to a layer 1. And you can make, this can be a layer 2, whatever, and there's lots of fun stuff you can do with this. Okay, this is a thing that got big like last year, the year before, something like that. Mina, it has the ZK rollup part. You have a bunch of transactions, you prove the transactions, but we don't stop with the transaction proof. The transaction proof folds into a block proof, and then the block proof also is recursive. So there's a proof of genesis, the proof of the next block, the proof of the next block, et cetera. And so what you get at the end is, we actually don't need a blockchain in the same sense. We don't need to store all the blocks. We can throw them out, and all we do is we keep this proof. So we invented ZK rollups, but just didn't call them that. Whoops. So we launched mainnet a while ago now, like 2021. And Mina is the first succinct blockchain. It's still the only one. And the nice thing with succinct blockchains is that the complexity of verification of the chain of things that are happening remains constant, even as the stuff that's happening is growing. It's O of 1 instead of O of n. O of 1 labs, get it? That's why we're called that. We actually, in Thailand, we were at a meetup and there was a fridge that had a computer on it. So we put a Mina full node on it. So this is the kind of thing that you want out of a decentralized network, that you want out of a Web3 system. You want it to be decentralized, and you want to be able, you can't be truly decentralized if it's not truly accessible. So this is just kind of like a toy, obviously, right? But it just shows like the resource requirements for running a full node, connecting it to the network. And this isn't a light node. There's no compromise here. Like, this is a full node security. It's small resource requirements, right? So this kind of leads us to another problem that I guess ZK solves. Most blockchain systems, they have like replicated computation. So when I'm running a DApp on Ethereum, my smart contract execution, it's happening on all the nodes in the network, not just at the moment that I send the transaction, but forever, anytime any node is catching up to the network, and that's just crazy. What we want is to run something once, right? And there's a lot of ZK products out there now that help enable this in different ways. And of course, we wanted to add this to Mina, so we did. So, and here's Vitalik talking about this. Yeah, this is Mina. So, okay, so we have, the transactions rolling up into blocks. When we first released Mina in 2021, you couldn't really do anything in the transactions beyond like very, very simple computations, payments, delegations, like toy applications. But we recently shipped a hard fork earlier this year that extended what you can do in a transaction to enable what we call ZK apps. And ZK apps, these are ZK proofs that prove a state transition, an arbitrary state transition on chain, which is sufficient enough to like do any application you want. And the particular, like the proof system and the tooling that we built is really, really friendly towards recursion. So obviously like Mina has all these nice recursive proofs. So we kind of like pulled that out and exposed that to developers. And so there's an SDK, O1JS. If you're a developer, you should try it out. It gives you like first-class access to this recursion. And so you can have your application and have your own recursive proofs inside of it. And that's inside of a transaction, and then that's inside of a block, and the block is just a single proof, or the blockchain is a single proof of a lot of blocks. That leads us to the proof singularity. It's a cool phrase. Where we have one single proof of everything that's ever happened, and the more that we put into applications on Mina, the more that we bridge into Mina, the more that this proof singularity absorbs all knowledge of everything that's happening in the world, and it can be attested to by this tiny proof that's super accessible that you can run on a fridge, or you can more usefully, right? On your phone, when you're trying to use a D app, instead of connecting to a centralized RPC service to access an application, in which case, like, what are we even doing? Is it decentralized? You can connect as a full node to the network from your browser without the user even knowing, and like truly access Web3 the way it was meant to be. So I'm happy to, if you have more questions about Mina, I can go into that. But I want to also spend some time. I have tons of time. Great. I want to spend some time talking about Project Untitled. So if you've been following me on Twitter, or if my tweet got retweeted enough, you might have seen this last week. So what is Project Untitled? Basically, we came up with a cool solution to a big problem and didn't have enough time to come up with a name. But essentially, the problem can be illustrated by this trilemma triangle. People love trilemmas in crypto. So here's the three things that we care about, right? Well, one is decentralization. Like, what the fuck are we even doing if we're not decentralized? Then, like, get out of this industry, like you have to care about decentralization if you're here, right? Like, and what does decentralization get us? Censorship resistance, liveness, and it's a value that we care about. Great, okay. But then the two other properties that we need when we're thinking about storing information for an application, I guess I didn't say that. We want to be able to store the information cheaply enough that we can actually store enough information that we care about. And we need to be able to update it and change it. Application state is not useful if you can't change it. So if any two of these, there's something that we can point to. Like if we have cheap storage and high decentralization, there's actually tons of projects that are doing this in Web3 that can archive data, but it's immutable. And if you try and update it, you're going to be very sad. If you have cheap storage costs and the ability to update it, then you have like AWS and Firebase and like a bunch of centralized things. And you know, a lot of people are using these centralized services for their applications, and they just store Merkle root on chain. But this is unacceptable, right? And then on the bottom here, like on chain, on a network, like let's just say Ethereum, like it's super decentralized. If you store the data on chain, you know, you can update stuff in your transactions, but it's so expensive. Like you can't store large chunks of information. It's just infeasible. So Project Untitled, it does all of these, right? It fits in the triangle. So it's an actual solution to the problem of decentralized, like mutable application state management. How does it work? Yeah. So, because obviously a lot of people have run into this problem, right? And I think most people were just like, it's impossible. We kind of accidentally stumbled on a solution. So here's how it works. Okay, the core of it is if you pick a polynomial commitment scheme very carefully, then you get a bunch of nice properties that you can use as the core of a storage proof. And I'll explain this. I have a lot of time. Great. So, okay, so like, I'm going to talk about like a vector commitment. So what is that? If I have a vector, so I have like some stuff, I can, this is not a very rigorous mathematical definition, but I can commit to that. And usually this C, the size of C is like really small compared to the size of all this stuff. And if I show you C, then later I can open C and show you this, and you can believe that, you know, whatever, by showing you C, like I've already kind of committed to all this data. I can't change it anymore. Forgive me for my hand-wavy definition there. But so a popular one that people might be familiar with is like a Merkle tree. That's one form of a vector commitment, a vector commitment scheme. So you put these on the leaves of the trees, you hash, and then you like hash all the way up, you know, until you get a Merkle root, and then like the Merkle root would be your commitment. But there's other kinds of vector commitments, and there's one that we use in zero-knowledge proofs. In most zero-knowledge proving schemes, I don't know. Someone can correct me later, but at least in the ones I'm familiar with. So called a polynomial commitment. Great, polynomial commitment scheme. So the way that this is used in zero-knowledge proofs, so bear with me. I'm talking about like circuit level ZK. Okay, so there's all these ZK VMs now, but we're going to think about the circuit. If I'm describing a ZK circuit, you know, I describe my program basically by, you know, effectively a bunch of constraints. These constraints get transformed and represented as part of the proving process as coefficients to a polynomial. And then there's a bunch of other steps that use the polynomial commitment scheme and do a bunch of other things, and out pops a proof. Okay. The interesting thing here is instead of having these what we put into the polynomial be a description of the program, we're going to put just a representation of state in the coefficients of the polynomial. Okay? And actually, some people have done this before. There's, I think, like EIP 4884 kind of does something similar for storing data. But the interesting insight is if you pick your polynomial commitment scheme carefully, where you have two properties, again, forgive me for my lack of mathematical rigor. This is a new project, and I'm the CEO. I don't know anything. There's ways in which you can pick one such that it's cheap to update multiple parts of the polynomial at the same time. And there's a way to have additive homomorphism. And this lets us interpolate random challenges, which is important for building a protocol. And I'll explain that in a second. So if you pick your polynomial commitment scheme carefully, then you can do cool stuff with the math to say, like, just give me, A, C, and Z of the data. And you can request that with like almost no overhead. You can even push, I guess I drew the arrow the wrong way. You can even push updates back with almost no overhead for any arbitrary random selection of the data. So, right, so when we have this, okay, we can build a decentralized application state protocol on top of it. So the idea is, let's say I'm on somewhere, Ethereum, whatever. I want to allocate 4 gigabytes of space, and I want to register it I want to like pay for it for 3 months. Okay, so my application goes to Ethereum, and then there's a small bridge. You can think of like a based sequencer type bridge. So, but whatever, let's elide there. And then there's a request to create some space. The network is made up of a bunch of nodes that are able to store data. If we make, I'll get to that in a second. And then, so sorry, you'll pay for like 3 replicas, let's say. You'll get an okay, and then over time you can also say, hey, I want to update the data, and then it can be updated, and at any time the app can directly ask the replicator node for some data. And there's also some edge cases to work out when like people aren't behaving, but you can read up on that later. And then the core part of this that actually makes use of these properties that I mentioned before is over time, the network is going to demand that these state replicator nodes, the nodes that are holding the state, they have to use the randomness generated by the network mixed into their polynomial commitment scheme to generate a storage proof. And then they have to sort of say, I'm still holding the data, I'll show you. I'm still holding the data, I'll show you. And if you do this frequently enough, then you can be sure that they're always holding the state and it's always available and it's able to be updated. And we have a little prototype, like on my laptop, there's like 2 seconds of constant overhead, and then it's 500 milliseconds per gigabyte to do one of these storage proofs. So, we haven't done much more profiling than this. It's like a brand new project, but I feel comfortable that we can go up to big enough state to do cool stuff. So, and then just one last thing before I'm about to run out of time. As I was saying, like we can build a decentralized network, and actually, what we're doing with Project Untitled is we're going to fork Mina basically, and use a lot of the Mina code, and build another succinct chain. And why is this important? Well, when we have another succinct chain, it's super easy to fold it into one another. So the proof singularity can now include proofs about application state storage. And there's a cool thing where a lot of nodes on this network, they have to store data. Like it's their job to store data and they get paid for it. And so if you fill up their hard drive space with blockchain data, then they have less space to service the needs of users. But when you have a succinct chain, then you minimize the amount of extra space that gets wasted. So anyway, I think it's pretty cool. So that's it. We're still doing tons of Mina stuff. We're starting to do Project Untitled stuff. This is a brand new project. We have a Twitter for it. I don't know what that QR code's for, but there's a Telegram channel too. Yeah, thank you. You can happy to talk about it more at the end. So thanks.